So first, what did William Knowles try? He tried a side chain alkylation. Okay, that's what he did. He had a group. Okay, where he introduced CH2CH star group on a on one of the alkyl substituents. Okay, and he got a 1% enantiomeric excess. Nothing to write home about. Okay, and later on he moved on to these chiral phosphine ligands. Okay, so you can see there's a phenyl group, then a methyl, and a N-propyl. Okay, these were the three groups, and he found something like a 28% activity, 28% enantiomeric excess. And that was very motivating for him. Did not find much of a difference when he went to the isopropyl. Okay, and then he all he's doing is he's tinkering around with the R1, R2, and R3 groups. That's it. And so in one place, instead of taking the isopropyl group, he decided to replace it with a cyclohexyl group. Okay? And this increased the enantiomeric excess to something like 32%. Okay, and then he had the phenyl group and introduced a second phenyl group, but now he took an anisole derivative. So there was an OCH3 group, okay, on this, okay, and he was able to increase the enantiomeric excess to 58%. Okay? And then finally, he took a cyclohexyl group, an anisole group, and a methyl. So all he's doing is just playing tic-tac-toe with the phosphine ligand. That's what he's doing. Okay, and he ended up getting 88% enantiomeric excess. And you can imagine the kind of excitement that it created, and all because of his understanding that he needs to have a chiral phosphine ligand. Now, I'll just read this out because it's important. Our first real variation was to introduce the ortho-anisole group. This should provide some steric hindrance as well as a possible hydrogen bonding site, but all pretty much hand-waving arguments. Furthermore, the ether linkage would be stable enough to survive the rigors of a phosphine synthesis. So he basically says that this is where he had his big breakthrough, that he was able to introduce the OCH3 group, and later on, the OCH3 group plus the cyclohexyl group and the methyl is what gave him that 88% figure. And he says it's interesting. It all seems too easy and simple, but this was the first time ever that anyone had obtained enzyme-like selectivity with a man-made catalyst. Never in our wildest imagination did we think a structure versus activity study would converge so quickly to a product with commercial potential. Camp, Camp is this, okay, was our sixth candidate. As I look back from this perspective, I don't think that even we were emotionally equipped to realize what we had done. Here, with the simplest of molecules, we had solved one of the toughest of synthetic problems. For the past 100 years, it had been almost axiomatic among chemists that only nature's enzymes could ever do this job. Okay, and he goes on to say Louis Pasteur stated in 1851 that dissymmetry is the only and distinct boundary between biological and non biological chemistry. Symmetrical physical or chemical force cannot generate molecular dissymmetry. Asymmetric synthesis in the laboratory made this notion no longer true. Now, I would say that Knowles has overlooked a simple thing. He's forgotten that how, in the first place, he made these chiral phosphine ligands. Okay? You make use of natural compounds like menthol, etc., which came from nature, And that is what was used, whether it was Kurt Mislow or anyone, that those natural molecules is what was used to carry out the separation. So it is not as if you really did it with no help from nature. Not true. You did. But again, if you go back to one of my earliest lectures, it is interesting to ask how, in the first place, nature actually made optically active compounds. What happened? How did the chiral bias come in our universe, in our world, that nature was able to make it chiral? There must have been a chiral force which made that happen. And in fact, my wandering mind tells me that, look, I mean, what kind of a galaxy do we have? Do you know? What is our galaxy?
Spiral galaxy.
Spiral galaxy. Okay. And what is spiral? Will it be a chiral force?
Yes, it will be chiral.
It would be. And it's very interesting that, look, when you are making a galaxy, okay, and it's a single event, so it had no choice. It had to either spiral clockwise or anti-clockwise, and it chose to spiral in whichever direction it did. Okay, but once it spiraled, our entire universe is a chiral force. I'm not saying that that is the origin of chirality in our world. I'm not trying to suggest that. But what I'm trying to tell you is that a chiral force does exist in our universe. And who knows, the first molecules may have come from somewhere else, the first chiral molecules, or they could have been made some other by some other unknown process. But I think once in a while, just let your mind wander. The second important lesson which I want you to learn from this is, if you look at the kind of intellectual capability that William Knowles had, I'm sure any of you have that. I do not have the slightest doubt, or maybe some of you would be even smarter than William Knowles. I know how bright some of you are. Okay, but what Knowles had, which you may not have, why you, I'm saying the majority of people will not have, is that kind of tenacity. That when I've got something like a 1% enantiomeric excess, most people will get so put off, and so demotivated that they will just leave the subject. But William Knowles had the tenacity to take it forward to 88%. And I have a feeling that William Knowles, had he been in academia, in an academic institution, he may not have done it. But being in an industry, people in Monsanto would have told him that, look, unless you get 90% enantiomeric excess, don't please come and talk to us. We are not interested. We will continue with our arrangement with Hoffman LaRoche. And so there would have been this kind of a motivation. The other very important lesson, which this particular Nobel lecture, which I want to leave you with, is that, see, I've seen there are a lot of people, okay, who are good at proof of concept studies. Okay, so they'll do something, they'll publish a paper. Okay, then they'll go and do it on another molecule, they'll publish another paper, and goes on and on. Okay, but I see an analogy between William Knowles's work and the work of Haber, on and Bosch on ammonia synthesis, that they were focused on one molecule. It's not as if William Knowles wanted to make thousands of molecules in a poor manner. He wanted to make one molecule well. It's not as if Haber wanted to use his high pressure synthesis for doing thousands of hydrogenation of nitrogen with hydrogen, he was just focused on ammonia. Okay, and so they had this single product focus. Okay, and it's very different from people who are just jumping from one problem to another, and in every case doing a minor proof of concept study. I would consider our towards chiral metal as that kind of I will say amateurish, flippant research, where yeah, I mean, fine. I mean, we made the first chiral conducting polymer. So what? What did I do with it? Okay. Did I make it well? Did I study the structure? Did I understand exactly what is the nature of the chiral disposition of the complex? Nothing. You know? And the little motivation that we had was when my company in the UK they got interested because they saw potential of this in making coatings, surface coatings, paints, okay, which might be able to evade microwave detection. That was the interest. It never went really to that level or beyond that. So I think you must be able to differentiate, people who do proof of concept studies and those who take things to their logical conclusion. Okay, and that's what I mean here. Most of the time I'm reminded of some of these dahi handi kind of things where most of the time you're just climbing up the pole and slipping down. Okay, and finally one person reaches the top, and and majority are just slipping and sliding and falling down. And most of the time, what we're doing is we are doing research at some stage here, okay, and we make great claims. We have done this, we have done that. Okay, but what I want you to learn is that technology attractiveness is all about moving up the learning curve. Okay, and this is the point where, for example, in the case of William Knowles, 88-90% may have been the point of technology attractiveness. Now, I've also seen a lot of people who, because they don't do this kind of work and they're not aware, they think that what they are doing is the most difficult part of the job. And they'll say, oh, what is there? After that, you just have to go here. Okay, and they forget, okay, that probably the larger part of the effort and innovativeness, goes actually at that point. You just have to look at the slopes of these curves. It'll tell you something. Okay? So I think that don't get impressed by thousands of these proof of concept studies, where again so many things are many times swept under the rug, things which are inconvenient, you just brush them aside. When you are developing technology, you better be focused on going to see, and that will provide you a great motivation. Okay, now let us try and understand. You see, up to here, what Knowles did was what I will say that he really, even though you don't need to be a super genius, but you do need to have, as I said, patience and tenacity to reach that kind of level. But what another thing that Knowles points out, and is that you can do all the work that you want, okay? And you might have put in a lot of effort, okay? But you also must have luck on your side. Okay? And Knowles gives two great examples of where luck was on his side. So what did Knowles start with? He started with this olefin, right? Okay. Now this olefin, when you have got three of these substituents, right? Over here, over here, over here, and the other is H. Okay, these types of olefins you don't express through cis trans. You can't. Okay, so there's a different nomenclature which have all of you heard of the E and Z nomenclatures? Everybody's familiar?
Yes, sir.
Yes, sir.
Fantastic. Okay. So since you know, okay, that when you have in both of the carbons, the substituent with the higher atomic number on the same side, okay, then we call that as Z. Okay. And if they're on opposite sides, we call them as E. You know. And what Knowles found is that in this process, when he got the olefin, it so happened that he was making the Z isomer. And that is purely luck that it did not give you the E isomer, it gave the Z. Why was it important? Because the rate of this hydrogenation reaction, the ease with which this chiral hydrogenation reaction took place was much better with the Z isomer compared to the E. Okay, and so he says prochiral enamides. By the way, one of the things that Knowles uses throughout his lecture is this term enamide. According to me, it should be called enamine. I've also talked to some organic chemists because you see the ene is connected to the amine group, is not connected to the amide group. So I don't think that enamide is the right nomenclature for it. I don't know, or maybe it could be. Somehow I'm not comfortable calling it an enamide. I think it should have been an enamine. Okay. Anyway, so what he says is that prochiral enamides can exist in both E and Z forms. The Z hydrogenates efficiently, whereas the E is less so. Both give the same product. Fortunately for us, the base condensation used in their preparation gives us only the desirable Z form. That's luck. And so this was one of his lucky breaks. Okay, that's not the only one. The second, which he talks about, which is interesting, all right, is that once Knowles had done this hydrogenation, okay, he realized that this is really he can make all kinds of amino acids, and which are the building blocks of all proteins. And so Knowles says R can be just about anything except carboxylic acid group. Lady Luck was with us, since if we had a choice where the catalyst would be useful, we couldn't have selected a more important area than the alpha amino acids, the building blocks of the proteins. So once they had cracked this problem of dopamine, you know, they realized, the sky is the limit. Okay, in applying this technology, because they can make all the amino acids in a chiral fashion. So I hope you can understand how important this invention was. Okay? Now, let me ask you the question now. Uh, let's go through again this scheme. I just want you to look at it. Okay? And you've also seen the chiral phosphine. Uh, just look at this. Now, what are we saying? That over here, we started with three of these of these phosphines. One fell off, but you can see that always there are two phosphines. Okay, at least two. Okay. Now, if you knew this, is there any other kind of change that you might be able to incorporate into the catalyst? And the hint, as I said, is that at any given time, at least two of these are present.
But like change for what? Like what is our aim?
Change means, see, I've already looked at, let's say, variants where you're changing the R1, R2, R3 groups. Okay, that's been done. Okay. Now, suppose I say that I'm not exactly satisfied and I want to go to 100% of enantiomeric excess. Okay. Uh, Uh, can I think of doing any other changes in this complex?
Sir, can't we like change the metal itself? Like, can't we
Okay,
use some other
yeah,
metal?
you could. I mean, and we'll talk about it later on. Okay, but for now, keep the metal constant.
So also like I don't think that if we replace chlorine with something else, it would matter that much. So,
Okay, keep that also the way it is.
so basically the phosphine molecules only like
Yeah,
that.
what can you do to the phosphine? By the way, I hope you will also see from these question answers that actually it's not so easy to come up with an answer to a question. You know? And of course, later on when you know the answer, it looks obvious. You know? But it's not so easy. And again, listen, you are too inhibited. Okay? You are too scared that you will say the wrong thing or say something absurd. As far as I am concerned, it doesn't matter one bit. So you need not be shy with me.
So but like if the two phosphine ligands are present at all times, like can't
Yeah?
we get rid of them entirely?
No?
Because
Uh,
I
you get
don't.
rid of them.
Yeah, because they are not like affecting the action.
Who said so they are not affecting? If you did not have these, you would not have the balance of the electronic properties around the rhodium. Okay, the reason why you have this H activation, etc. If I just take rhodium trichloride, you're not going to do it.
Sir, so can we like use this molecule since only one of the phosphines is falling off? So
Yeah.
can't we cause the other ones also to fall off and do
No,
some
why do
other
you want
action?
it to follow? I've made your life simple. I said let's assume that they are important and they should stay there. I am asking you with that knowledge, okay, can I bring about any other change?
We modify the phosphines.
Yes. How?
Sir, that
Go a
new
bit further.
the new one that is coming in, we put a different phosphine. Say we put a methyl group or
That's one. Let's say I fixed my R1, R2, R3, and I don't want to change it. I mean, no. I mean, I might want to do it. I'm not saying no. That could be one. That you take two different phosphines, with two different R1, R2, R3. Right? That's what you're trying to say, isn't it? Huh?
yes, but that new one we will put chiral so that
No. Why
in the
new one?
K3.
Even the other one is chiral, no?
Yes.
Any other. And when I tell you, you'll say, of course you can do
Sir, can we use some other ligand instead of the phosphine?
it. You mean not a phosphorus ligand?
Yes, sir.
No, I don't want you to do that. I'm reducing your degrees of freedom. Okay? Otherwise, I can go wildly all over the place into discovery research.
Yes, sir.
You understood? Huh? When I've narrowed down, okay, I don't again open the funnel and make it completely invert it and make it go all over the place. Okay. Can I have a bidentate ligand? Yes or no? A
Yes, sir.
bidentate phosphine ligand,
Yes, sir.
Yes.
right? I mean, that is the kind of change where you're not talking about extreme changes. You understand? So within a very narrow room for maneuver, although, I mean, I'm not saying that in all cases that would be the case, but when you have got still some degree of freedom, first exhaust that. If things still don't work out, of course you will go to something else. Okay, but don't straight away go into a completely different dimension. Play around with whatever degrees of freedom you have. Okay? So this is where there was a conceptualization of chiral bisphosphine ligand. There is something remarkable about what Kagan did. You know, I think that his way of looking at the thing was different. He wasn't looking at it exactly the way that I asked you the question. You know, what Kagan probably was trying to do was challenge his basic hypothesis of Knowles that to get good chiral induction, that you need to have chirality around the phosphorus. Because that he's been saying this, that we felt strongly that if one wanted to get high enantiomeric excess, the asymmetry would have to be directly on the phosphorus. That means chiral phosphine. Okay? But probably Kagan did not think so or challenge that. And how did he challenge it? Okay? What he did was that Kagan, and also, you know, there could have been also a sense of patriotism. Okay? Just like Louis Pasteur, who is the father of chirality, who and what were the molecules which opened up this area? It was tartaric acid, right? Right or wrong?
Yes, sir.
Yeah. So Kagan may have said, hey, I get tartaric acid from nature, which is chiral. And another reason could have been that, I mean, Knowles has not told you, but I'm sure making that chiral phosphine ligand is not such a simple synthesis. That resolution, etc., I'm sure it's a difficult job to do. Okay? And whereas I'm getting tartaric acid on a platter from nature. So, what then Kagan did was that he said, oh, let me, if I can somehow, right, you can see like this is the carbon and this is the carbon. These are the chiral points here. Okay. And then, of course, you've got your OH and OH. Okay. And he would have probably said that if I reduce these carboxylic acid groups, you know, and then maybe I'll be able to then carry out a reaction with some phosphorus derivative, okay, and I will introduce the phosphorus one here and one here. Has everybody understood the structure? You understand that this is the same as this, okay? Okay, and these are the two oxygens of that which I'm tying up, okay? Maybe with acetone, you know, and I'm getting this kind of a rigid structure. And over here, these two are being basically converted into these phosphine ligands. All clear?
Yes, sir.
All clear, isn't it? Huh. And now look at it. We have departed from Knowles. I don't have chirality now around my phosphorus because I've got two same phenyl rings. Okay, and Kagan used tartaric acid, as I told you, readily available, and with that he was able to get an enantiomeric excess quite close to what Knowles had reported, that 88%. Okay? And Knowles says it in a beautiful style, and so I'll just read it out. At the time of our initial commercialization, we learned of a new efficient ligand invented by Professor Kagan, which he called diop. So this ligand is diop. This was a chelating bisphosphine made from tartaric acid with chirality on the carbon backbone, and it gave results comparable to CAMP. We had hypothesized that to get good results, one needed chirality directly on the phosphorus atom. It made sense, but Professor Kagan showed us to be totally wrong. It is most appropriate that this invention using tartaric acid should have come from a Frenchman in the land of Louis Pasteur, who, of course, was the one who got it all started. I hope you can also see how beautifully they write. Not only are they great scientists, their articulation, their ability to write is so admirable. No? I hope this is another thing that all of you will learn from these Nobel lectures. Beautiful articulation. Kagan's discovery was the wave of the future for a whole series of bisphosphine ligands with asymmetry on the chiral backbone. It was on the backbone. Okay, and so this is how, when everybody is veering towards in one direction, and everybody would have said phosphine chirality, and then another person magically changes all that and says no phosphine chirality. Chirality can be in the backbone. Now, frankly, if you ask me why Kagan did not get the Nobel Prize, I don't know, because I really feel Kagan's work was of great importance. Okay. The second thing William Knowles mentions about another lucky break. You all will appreciate this, that from an engineering end, to be able to finally recover a pure compound is very important. And obviously, when he is getting something like 88% enantiomeric excess, that's what he had got. Okay, what that would mean is that you would still have something like maybe about 6% of the other isomer. Okay, so then of course 6 and 6 is 12. So that's what is racemic, and then 88% is enantiomerically pure. So that's what enantiomeric excess is. But these things are not so easy sometimes to separate out. Okay, and he says that he was extremely lucky that the manner in which the hydrogenated product crystallized out, it made this resolution easier. Okay, and I'll try and explain this a bit more, but let me tell you, read out what he says. Even in the best case, some racemic product is made and must be separated. Okay, so it was about 12% was racemic. Okay? This separation is easy or hard depending on the nature of the racemate. If the racemic modification has a different crystalline form than pure D or L, then separation of the pure excess enantiomer will be inefficient. If one achieves a 90% enantiomeric excess, then it is possible to get out easily only 75 to 80% pure enantiomer. Okay, with the lower E's, the loss becomes prohibitive. So if you have something like, let's say, a 75 or 80% enantiomeric excess, you might think that you've done a great job, but really sometimes resolving it becomes next to impossible. Okay? Now, then he says, with lower E's, the loss becomes prohibitive. For such a system, a catalyst of very high efficiency must be used. Unfortunately, most compounds are of this type. This type means the one where the raceme is of a different crystalline form than the pure isomers. If, on the other hand, the racemic modification is a conglomerate or an equal mixture of D and L crystals, then recovery of XL-L can be achieved with no losses. Since the L and DL are not independently soluble, as 90% E easily gives the 90% recovery of pure isomer. In our L-DOPA process, the intermediate is such a conglomerate and separations are efficient. This lucky break was most welcome. If one thinks back, ours was the same luck that Pasteur encountered in his classical tartaric acid separations 150 years ago. But let me also tell you that Pasteur actually did not separate tartaric acid. He separated sodium ammonium tartarate. That was the salt that he actually was able to separate, not tartaric acid, and I'll show you why that is the case. Okay, so let us quickly understand, just so that you have a better feel for what is meant by these terms. Okay, now many optically active compounds, they have the property that when you get a crystal, the enantiomer prefers itself. Okay, so when you get the crystals, even though it's racemate, it's actually a pure enantiomer crystal and a pure opposite enantiomer crystal. Okay, and the two together, of course, will give you a racemate. But the individual crystals are actually optically pure. So where you have that, that's the kind of luck that Louis Pasteur had, that he was able to separate those out. A racemic compound, which we say is a true racemate, basically what it means is that an enantiomer loves the opposite enantiomer. And so individual crystals are racemic. Okay? So that is known as a true racemate. Okay? Whereas this is known as a conglomerate. Okay? So what he is trying to say is that the majority of compounds that one gets tend to be of this form, where you get a true racemate. And these are the ones where actually separating out a pure enantiomer, even if you have a sizable enantiomeric excess, is more difficult. Whereas when you have a conglomerate, it becomes easier to separate it out. Okay. Then there are of course variants like a pseudo racemate, where the interaction energy between the opposite enantiomers and the same enantiomer are not that different. And it's also very interesting that if you have like a conglomerate where you have got these pure enantiomeric crystals basically mixed together, you can look at it as if one enantiomer is like an impurity on the other enantiomer. Okay, and there when you are adding the opposite enantiomer, or you can say that the racemic conglomerate will always have a lower melting point, than what the pure enantiomers will have. Okay, in the mixture. Whereas in a true racemate, it could go either way, because the crystals behave very differently. Okay, in the two cases. Okay, so these are very, very subtle differences, and they were first actually categorized by this person Roseboom in 1899. Okay, but remember that a lot of the technology is related to separation technology, and understanding all these interactions is very important. Okay, just remember that. Now, just to give you an indication, that suppose, let's say I take pure tartaric acid, pure enantiomers, okay, and you can see what is their melting point, 168 to 170 degrees. That's the melting temperature for both of these. Now, interestingly, the racemic tartaric acid, okay, has a melting point of 206 degrees. Now, so therefore, if it is 206 degree, what type of a racemate are you forming with the racemic tartaric acid?
So it's a true racemate.
It's a true racemate, okay? Because otherwise the melting temperature would have been lower, okay? And so this also tells you that actually what Pasteur separated is not tartaric acid. He could not have, because each of the crystals would have been racemic, okay? And so it's so interesting to actually figure these things out, okay? And then of course you also know that if you write the tartaric acid form, I mean, from the structure, you can also get a mesotartaric acid, okay, which is a different compound. It's like a diastereomer, and so that can have any melting temperature. So may not have any relationship with any of this. Now, what is also very interesting, just have a make a note of this. Look at the solubility differences. Okay, this racemic tartaric acid is much less soluble than the pure enantiomers. Seems hard to imagine, but that's true. Okay? Now, in fact, there was a time. If I get the opportunity, I'll tell you about the origin of the work. But there was a time when we had actually exploited knowledge from around the 1930s, which was an quality control test at that time for potassium, and where potassium actually, in presence of tartaric acid, precipitates out as potassium bitartrate. And we thought that why can't the analytical test be actually used in a process? And that led to a very nice process. Now, what was very interesting was that when we were recovering the potassium bitartrate, and then we had to recycle the tartaric acid, and we developed a technology whereby we converted it into an intermediate compound, magnesium tartrate, and then it was easy to actually work out the scheme, and that then became the technology. It's got a huge potential. And I remember at that time, I asked my colleagues who were working, including my student, I said, hey, why don't we just see what happens? Suppose I take racemic tartaric acid and L-tartaric acid. What happens to this magnesium tartrate? Do we get the same kind of behavior or a different behavior? Okay. The particular reason for actually being interested in the first place was this high solubility. So we knew that we can actually work with concentrated solutions if we take the pure tartaric acid. And also there wasn't much of a difference in the price between a racemic tartaric acid and the pure tartaric acid. So it didn't matter. We could have used a pure tartaric acid. Now, what was extremely stunning when we looked at these things in the microscope were completely different morphologies of the crystals. Like magnesium L-tartrate was more cubic type of crystals, as you will see here, whereas this DL tartrate formed this needle-like crystals. And in fact, it was very interesting that some of it was like a cross. You can see these crosses, okay? And so it looks like actually it formed like a cross, and then the crosses broke up into these rods. Most probably that's what happened. You can imagine that suppose let's say make these solids, and then I want to filter it out. This will form a very dense cake, whereas this will form a very porous cake, because when these rods are all put together, there's sufficient porosity in the filter cake. Okay, and what we found is that this was actually much easier to filter. The filtration rate was very efficient. The second is, because the filtration rate was very good, we also found that the moisture retention in this magnesium tartrate was very low, because the wet cake released most of its water, whereas this one it tended to retain a lot of water. So actually, it's very interesting that this was in fact one of the first examples where we are not talking about chirality and using it only for as a drug or because of its mode of action in biology. It could be that it can directly impact on process, as it was in this particular case. Keep that in mind, that when you're looking at these kinds of problems or things that come your way, always ask yourself, can I do some simple experiment and just see what happens? I mean, initially we just did it out of curiosity, nothing more, But that the crystal structures would be so different, and that it would have a direct impact, a bearing on the filterability and the moisture retention was important. So in our case, finally we decided to use the DL tartrate, in carrying out all this, because also the DL tartrate was a little cheaper than the L tartrate. So I hope you can see, how these things sometimes go. Okay. Now, let me also show you, going from beyond the work that initially Kagan talked about and Knowles talked about. Knowles, of course, recognized that Kagan had basically got very good results, even when the chirality was not on the phosphorus. But then what Knowles did was that he married the two concepts. He married the concept of Kagan. He said that when you have a bidentate ligand, the results are really good. Okay, and he did not want to give up his chirality around the phosphorus. So basically, what he did was that his initial monodentate phosphine ligands, okay, he started converting into bidentate. So earlier he had made these kinds of ligands. You will remember methyl, phenyl, and this anisole. Okay, and in another case, which gave the best result, it was methyl, anisole, and cyclohexane. Okay, and so he developed a strategy of making a bidentate form, but again keeping a chirality around the phosphorus. And what they did was that he was able to get now a 95% enantiomeric excess. The best he had got before was 88. So clearly there was an effect of both the bidentate form as well as the chirality around the phosphorus, and that's what he was able to prove. Now, this is again something which is important. The particular product that he made was not the one which actually gave the best result. The best result we had seen with the cyclohexyl derivative, not with the phenyl. The phenyl one, this one, the monomeric form had given just 58% enantiomeric excess. So basically from 58%, it jumped to 95% by making it bidentate. Why did he actually not work with the cyclohexyl? He says that he preferred this because of practical reasons. And the reasons were that it was easier to synthesize. And second, he says that he got a much more stable, air-stable, very nicely crystalline solid, much easier to work with. And that is the reason why he abandoned CAM, which otherwise had given the best result, and went back to PAM, the phenyl, anisole, methyl. And in fact, a lot of innovations are really about marrying two ideas, and you tend to get, sometimes it's not always that you will get it, but that is again one of the degrees of freedom which you must always try and exploit. Okay. Now the other thing, which he did, and this reminds me of many times, like Russell Lowell and parting with the battery altogether, and then finding that it's still generating electricity. Now, when you have made, and especially an organic chemist, when he has made these kinds of compounds, okay, that person does not want to do anything drastic with these compounds. Okay, and you can imagine with the phenyl, etc., these compounds would be typically not water soluble. So his catalyst was not water soluble. It would operate only in organic solvents. And one day, one of his assistants, he says he came in the morning and was shocked. And the guy had actually treated this catalyst with oleum, okay, to do a sulfonation, okay, and ended up making a sulfonated product. Why did that person do it? Simply because once I sulfonate, the catalyst becomes water soluble. Okay, and he says, in fact, in a very humorous manner, we could sulfonate dipam and make it water soluble. I winced when I came in one morning and saw our valuable dipam being treated with concentrated sulfuric acid, but it worked. And there was also no reason for it not to work, because really the only reactive site over here for sulfonation is the aromatic ring. And once I've sulfonated it, it becomes water soluble, and then it completely opened up the area again, that you could do asymmetric synthesis in aqueous phase. So I hope you can see that these are all examples of you do something very, very small, and the implications then are massive, cutting across so many different opportunities. Okay. Now, people, of course, also don't give up just because you have got 95% enantiomeric excess. And I'm sure a lot of other companies were working on this. It's not as if only Monsanto and Kagan were working. And quietly, DuPont was also working in this area. And DuPont had some of the best chemists. And they came up with this structure. Actually, in some ways, it's a much more elegant looking bidentate ligand. Still bidentate, remember. Okay. And this eventually gave this greatest of accomplishments, that they were able to achieve 99% enantiomeric excess. Take yourself back to 1% enantiomeric excess with a side chain chirality, and ultimately ending up with a 99% enantiomeric excess. And that's what I mean by sense of perfection. Okay? Now, why was it important? Because all your crystals are not going to be of the conglomerate type. You may actually form true racemates. And if you have got true racemates, unless you have a very high enantiomeric excess, your losses will be high. So now probably DuPont didn't care whether you made a conglomerate or a true racemate, simply because they were able to achieve such a high level of enantiomeric excess. Okay. So that's what was done. And I hope you can also get a feel for how, when it's an important area, that how many organizations and companies are simultaneously, parallelly working. They may not have been the leaders. Right? They were not the originators. DuPont did not conceive these ideas. But ultimately, it is DuPont that probably won because they ended up getting the best ligand. Okay. Any questions? Is it all clear for everyone? Do you understand?
Yes, sir.
Okay. All right. So with that, I come to the end of William Knowles' lecture, but by no means the end of asymmetric synthesis. And Knowles actually concludes his lecture again in a very interesting manner. And he says, for an invention to succeed, Paul Ehrlich, the father of chemotherapy, has stated that 4 G's are required: Geist, Geduld, and Gluck. The first of these is axiomatic. And he says, you have got to have a good idea. And in his case, that good idea was that he can modify Wilkinson's catalyst to make it chiral. That's the good idea. After that, everything was labor, a lot of effort. After that, it wasn't really a good idea. It was effort. The good idea was the thought that why don't I make the complex chiral? The second is essential. One needs financial support. You need some money, to carry out your work. But he says, what he said earlier, but I would suggest a proper balance. Too much or too little is inhibitory. And believe me, I have this feeling that nowadays, with all this glut of instruments, fancy things, etc., actually we have got mired in sophistication. It all looks great. It's like a very well-dressed person. Okay, but the core idea may not be so great. Okay, and so that's what is happening. There's a lot of dazzle. Okay, but not necessarily a very good idea. Okay, and then he says for the third, okay, it's extremely important. Patience. Okay? And this is where I think that the majority of us will fail the test. We don't have patience. We think that we have done something. We don't have the patience to take something from 1% to 100%. And also, look, they were lucky and they got. You might be working all your life and may end up nothing. Okay? So the question is, whether you have that kind of a patience, you'll have to look at. And the fourth, of course, and he has given ample evidence of that. He says you can do all of this. Okay? But if you do not have luck on your side, it might all be futile. Okay? And for him, he said that certainly in the early stages, his luck, okay, was the fact that it was quite a general procedure that he had developed, could be applied to many alpha amino acids. The second is that he got the Z isomer, which made the hydrogenation much easier. And the third was that he ended up with a conglomerate. And let me tell you that even while we might be applauding Knowles, I'm sure Knowles was fighting a battle within his company. The company would have said, hey, we are not so impressed with your 88% enantiomeric excess. We will continue to go to Hoffman-LaRoche. And they would do it simply because, the separations would still lead to a lot of waste. Okay, I'm sure he was fighting this battle. I'll show you when I'm talking about one of the hard drugs. After they'd done everything, okay, DuPont, again, it was a case of DuPont, okay, they said, no, we are not going to commercialize this. And I can tell you the kind of frustration that my roommate and everyone felt that what, after doing all this, you're not going to commercialize it? And they said, no. But these guys were bold enough that they went to another company, Merck, and they that led to a tie-up between the two companies, DuPont and Merck. You see, Knowles is not the only one who was working right on this. The Japanese were pioneers in asymmetric synthesis in a way, and Noyori had plenty of experience. So Noyori also started looking at it. It was really a Me Too approach. Everybody was all the people were following Kagan, okay, and making bidentate phosphine ligands, okay, and again working with rhodium compound, and ended up trying to see what kind of a result they get. No different from what DuPont was doing, okay, but where Noyori scored is that Noyori looked at the ligand in a very different way. Okay? And the kind of chirality that he looked at was neither the chirality of tartaric acid nor the chirality of the phosphorus, the chiral phosphorus, But what Noyori ended up doing was making these kinds of compounds. These are called the binaps, and these two naphthalenes, they can be on one direction or the other with respect to each other. They're twisted, okay? And so you can get two enantiomers of these binaps. They're twisted compounds, okay? And and these typically tend to have very high optical rotations. And so that must have been something that probably interested Noyori, that maybe he'll be able to get a better chiral induction with these kinds of compounds, But you can see the rest of it is similar. Now, so Noyori says in his Nobel Lecture, to discover high-performance asymmetric catalysts, developing an excellent chiral ligand is crucial. Of course, attracted by its molecular beauty, we initiated the synthesis of binap. Now, he is again talking about what appealed to him was the beauty of this binap. But that might be more to impress people during his Nobel lecture. But there's no doubt about it also that binaps are very elegant looking compounds. So there is a molecular beauty, no doubt about it. And so Noyori then basically began uh, testing these ligands out in a wide variety of reactions. Noyori had another big advantage, like Knowles, that although Noyori was not in an industry, Noyori was in an university, but in Japan, they have extremely strong interactions between industry and academia. This company, okay, Takasago, okay, is a very pioneering company in Japan, and Noyori was actually working with Takasago, and many of the compounds, which people thought only nature can make, and the irony is that they use natural compounds like menthol, okay, to do all the initial separation of all these phosphine compounds, starting from Mislow and Horner. But later on, they were able to use the artificial catalyst to actually make menthol. That's remarkable. This is really wonderful. And so he gives over here, the scheme by which they ended up making menthol. I'm not going to go through the whole thing, but crucial in this process was that basically they were forming something like an enamine first, and then the most crucial thing was that they were able to do a hydride shift, from one carbon to another. Okay, and so this is the hydride shift that they got. One hydrogen went here, and this was a chiral center, this particular carbon. Okay, that's what they ended up doing. This was your chiral center. Then they basically hydrolyzed the enamine, got back aldehyde, and from that, okay, they were able to make menthol. You can go through the whole process, but it was remarkable. It was not really a hydrogenation, but a hydride shift. Now, Noyori was also very versatile, and I think that was probably because he was in academics, and probably had a lot of students, and so probably he had to give many different projects to his various students, and so that's how Noyori expanded, okay, in terms of carrying out work. Now, we've also seen people like Haber, how they were able to shift, like from iron catalyst to osmium catalyst, where he moved down the periodic table. Okay, so periodic table has always been a source of inspiration, and I suspect, that Noyori began looking not just down the periodic table, but also started looking a bit sideways. I think it took things like rhodium and started looking either way at palladium and ruthenium, and must have asked himself the question, what's so holy about rhodium? Can we not work with ruthenium? Okay, and one of the reasons would be that ruthenium is a cheaper metal than rhodium. Okay, now something dramatic happened. Okay, when he did this, and so he says that a major breakthrough occurred when we devised the binap ruthenium to dicarboxylate complexes in 1986. Okay, so all he did was substitute rhodium with ruthenium. Okay, and he says the ruthenium complexes are excellent catalysts for asymmetric hydrogenation of various functionalized olefins. Okay, an important application is the synthesis of the anti-inflammatory drug naproxen. You remember that we talked about naproxen and how one of the opposite enantiomer is actually toxic to the body and has other side effects. Okay, and so I mean that was something which was interesting. Okay, and so that's what Noyori did. He just changed over from rhodium to ruthenium, and this was one of his biggest triumphs. That he was able to make this drug naproxen. Okay, The other thing is very interesting, that he was able to also look at these kinds of olefins. Okay, these are exocyclic double bonds. It's external, okay, over here, and you can see that the prochiral center. This is still a prochiral center. So these are the kinds of olefins that he was able to reduce. That's what he did in the case of naproxen. Okay, and that actually greatly expanded asymmetric hydrogenation, following this binap type of compounds. Okay, once he was ruthenium. Now let me ask you. So he had this. Let me ask you the question: can you see any other opportunity for making any variant, small changes, and testing out? Like he made a small change. He went from rhodium to ruthenium. Can you think of any other changes that you might be able to make?
Sir, like last time also I had suggested, like instead of phosphorus based ligand, we can use some other ligand.
Instead of phosphorus, that would be a big change, because the phosphine is such a important part of the coordination. I'm talking about relatively smaller changes, because you have to see that so many people have worked with phosphine. Okay, and so phosphine got embedded. If you go into others, you can, but you will be going back into hardcore discovery research. Any other changes that you can think of?
So then we can replace that acetate only. Then there's nothing else.
Which one?
The OAC that we have.
Brilliant. Okay, and I believe that one of you had even suggested this last time. That because that chloride, you remember, you said that can we put fluoride instead
Yes,
of
sir.
chloride, if I'm not mistaken. Am I correct?
So, I think I had only said that we
Yeah,
could
so in a
replace
different
chloride with
context,
something else.
but you did. Okay.
Yes.
Can we make simple changes? Vary the carboxylate. In other words, look at other anions. Okay, instead of that, because this is not so difficult to do. Okay, I just have to change the that anion. I mean, I'm not changing the basic molecule otherwise. Okay, now this is again luck, but Noyori never talks about luck. He talks about doing these things in a systematic way. Now, what happened was that when he changed the carboxylate to halide, okay, simple. I think he went to dichloride, or dibromide, things like that. Okay, it was a dramatic transformation that took place in the catalyst. And what happened was, up to that point, you see, I mean, people were always reducing olefins. Okay, no one had been able to reduce other functional groups. Okay, now by this simple changeover from a carboxylate to a halide, what happened was that now they were able to reduce the carbonyls in presence of other functional groups. I mean, so complete shift, okay, from the olefin hydrogenation, which they could do with the ruthenium carboxylate and rhodium carboxylates. Now they could actually reduce the carbonyl compounds. And once you can do that, it's mind-boggling the variety of organic compounds, of very important compounds that you can make, and where this carbonyl actually is a prochiral center. Okay, so he ended up making a wide variety of these compounds, and not only that, he was able to make them with very high enantiomeric excess, okay? Something like 99%. So let me read out over here what he says. Importantly, the list of substrates can be extended to include various ketones as generalized in figure 11. The halogen containing binap are due to complexes, but not the diacetate complexes. are efficient catalysts for the asymmetric hydrogenation of a range of functionalized ketones, wherein coordinative nitrogen, oxygen, and halogen atoms near CO functions direct the reactivity and stereochemical outcome in an absolute sense. So, what he thinks is that things like the halogens actually had a bearing on the electronic properties around the carbonyl. A wide variety of achiral ketones are hydrogenated enantioselectively to the corresponding chiral alcohols in 90 to 100% enantiomeric excess in a predictable manner. I'm not sure about the predictable. Now, this is very interesting. The reaction can be performed normally in alcohols with up to 50% substrate concentration. Just imagine, many times, when you're doing experiments in the laboratory, I've seen, people will dilute the raw material, starting material, to very dilute solutions and carry it out. Maybe sometimes because the starting material is costly. Okay, but if you're doing it in industry, you would want to maximize the throughput. You'd like to maximize the concentration of your substrate. So they could take 50% substrate concentration and 4 to 100 atmosphere pressure, which was not so difficult. And mind you, look at this substrate to catalyst ratio of 10,000. Because this was very important, these catalysts are not cheap. They're quite costly to make the binap catalyst. Okay? So you cannot do it if, for example, if you're going to work with a substrate to catalyst of 100:1 and after that your catalyst goes dead. So you obviously can do these kinds of chemistries only when you have got a very high substrate to catalyst ratio. We will also look at this when we go to Sharpless's lecture, later on. Okay, and they could just do it at greater than 100 kg scale. It was that easy to scale up. So I hope you can see. And the reason why I'm telling you this is, look, you may not be lucky if you bring about this kind of a change. Okay? But remember, try to always do the easiest things. Don't try to do the most difficult things first. After you have exhausted all the easy things that can be done, of course, by all means, do the difficult things. Like if you want to change the phosphine ligand, go ahead. Do it. But when there are easier things to do, like replacing a carboxylate with some other anion, do that first. And this is again something I urge you, and I see this a lot of times. That for whatever reason, when you have a tree with a lot of fruits and a lot of low-hanging fruits, for whatever reason, people don't want to pick the low-hanging fruits. They say, I want only the fruit at the top of the tree. Don't give me the fruit, even though you can just pluck it. Is that easy? And I think that's a case of great folly. And let me tell you, maybe a lot of times people who are in fundamental research don't look at it because they will say, it's too obvious, I don't want to do this. Okay. But if you're looking at innovation, and where by definition, innovation is that I do something extremely simple and that I get a tremendous leverage, a multiplier effect, then please do that. Okay. And otherwise, I would have titled this as complex reactions in chemical technology. That's not what we have titled it. We have titled it as innovations in chemical technology. So try to do simple things before you do complicated things. Okay. Now, so and I've just put over here, switching from diacetate to dihalide, the behavior of the ruthenium binap catalyst changed entirely, and it now became selective towards carbonyl reduction. Okay. And note the high E, exceptionally high substrate to catalyst ratio, and easy scalability. Okay. That's what you want to do. Many of you who are chemical engineers, this is what should appeal to you. That you go ahead and try such things. This is a very important one that he was able to make. One of the very important compounds, is this compound levofloxacin. And it looks simple. The basic crucial important intermediate is this R12 propanediol, which people were struggling to make before in optically pure form. But when Noyori could, reduce the carbonyls, okay, and in presence of other functional groups, he was able to make this almost absolutely pure. Once you could make this, the making the levofloxacin after that, although it's a multi-step synthesis, all that was very known chemistry. There was nothing new about it. The crucial break was really this, and that's what he was able to achieve. So again, when you are looking at a complex synthesis, okay, and I'm sure many of you, those who are going to go to industries, etc., you might be involved in this kind of work. Okay, always look at where is the shoe pinching the most. Where is it hurting the most? Tackle that. And in this particular case, it was this. There's no point putting in a lot of effort in all of this if you have not basically addressed this. Yeah.
One small doubt. So, like from rhodium, they switched to ruthenium, but
Yes.
why not like others? Like
I'm
previously, we
sure
had
they
seen.
switch to others. You see, in fact, this is another thing, okay, that people don't always report the things which didn't work well. What was negative, okay, and in fact, it reminds me. There was a friend of mine, John Beecham, in England, and John, when he used to show me his photographs, all the photographs always look so beautiful. I used to tell John, I wish I could take photographs like you. They're so beautiful. And John said, that's because I tear up all the bad ones, And that's effectively what these guys do. I mean, I'm sure they tried some of the other elements. Probably they didn't work. Okay.
Okay, sir.
With that, we come to the end of Noyori's lecture. The next one that I will cover, and for which half the Nobel Prize was given. Okay, so obviously it was considered to be very big. Was asymmetric oxidation. Hydrogenation, a lot of people were working on. And I think that Barry Sharpless was very smart, and he recognized where there is space for innovation. And he realized that oxidation reactions are relatively more neglected. Okay, and probably that's the reason why he went into it. So he always wanted to do something which nobody else was doing. Okay? Sharpless actually begins his lecture in a very interesting way. Okay, and as I told you, all of them write very beautifully. Sharpless was originally from South Africa. That's where he was born. That's where he spent much of his young age, and then probably shifted to the United States, like many of you will be doing. Okay, you get your basic education here, and then after that you're shifting there. Okay, he says this, and I thought it was quite nice, and I hope that some of you will at least relate to this. In 1938, 3 years before I was born, a live coelacanth, this is the spelling by the pronunciation, coelacanth, okay? And it's also known as the dino fish, constitute a now rare order of fish, was taken from the waters of the eastern coast of South Africa. Previously known only in the fossil record from some 100 million years ago, the coelacanth and the implications of his discovery remained big news for years. Now, can you imagine that when somebody thinks that something is extinct and it's only in the fossil records, and you suddenly see it jumping out of the water, or it's like people used to talk about the Loch Ness monster. Imagine if really a monster like that came out of the water, and so that's what he's talking about, and so it created enormous excitement. Okay? that you have actually this dino fish which people thought was extinct was there. I grew up loving the sea and loving fishing in particular. But unlike most fishermen, I cared less for the size or quantity of the catch than for its rarity. Nothing could be more exciting than pulling a mysterious and hitherto unknown creature from the water. As a kid, I passionately wanted to be one who caught the next silakan, the first to see something that was beyond reasoning, even beyond imagining. No? Now, I think that that is the kind of aspiration which I hope that some of you will have. That that can I do the unexpected, okay? And that's what spurred him on. Essentially, all my chemical investigations are in only one area, and I tend to view my research not with respect to projects, but with respect to where I've been driven by two passions which I acquired in graduate school. I'm passionate about the periodic table, okay? And he mentions the particular elements because these are the elements that brought him fame. Okay? And I'm passionate about catalysis. And he says, look, after that, where I apply it in which project, that's not so important. Okay? But these are the kinds of things that I'm most passionate about. There are two very fundamental reactions, of course, in organic chemistry. Of course, there are many more, but one is really reduction and the other is oxidation. And then, of course, you have things like bond formation, carbon-carbon bond formation, which we'll talk about subsequently. Okay, but these are really some of the very crucial transformations which are important. And especially when a molecule has certain centers, where some kind of a chirality can be bestowed after introducing functionality, then of course it opens up the opportunity for asymmetric synthesis. Now, Sharpless was really interested in this particular area of oxidation, and Sharpless actually not drew on, but I think that he was inspired by the same kind of thing that Kagan was inspired by, which was that instead of making all these synthetic chiral compounds like Knowles and Noyori had done, okay, he must have thought that why don't we use things which are readily available in nature, and that's always a very good starting point. Okay, so obviously the most common and popular is tartaric acid. Okay, and now, but there was a reason why he got into this area first. Okay. What was known was, Sharpless is one of those you'll find who drew extensively on old literature. And so in the old literature, it was known that some of these metal ions, when they do reactions with organic compounds, that there are certain ligands which seem to promote acceleration of the rate. Okay, and it used to be known as the ligand acceleration effect. Okay, LAE. And so he was working with titanium. Okay, and he had he was successful in carrying out an epoxidation first with these kinds of titanium compounds and using an oxidizing agent like hydroperoxide. Okay, and then he thought that why not use some of these ligands to accelerate the rate of the reaction. That's what he wanted to study. Okay, and then he thought he had the clever idea that look, I mean, instead of just putting any and every ligand, why don't I consider tartaric acid itself as the ligand? Okay, and after all, it's chiral, and tartaric acid has the advantage that you can actually buy commercially both the minus and the plus forms of the tartaric acid. So whichever isomer you want, suppose you're getting the wrong isomer, just change the tartaric acid to the other opposite tartaric acid, and you'll probably end up with the right stereochemistry. Okay, so that's what he did. It was a very, very simple idea, So whatever he was doing, where he was taking some titanium compound, and by the way, this compound owes its origin to a very famous Indian scientist called R.C. Mehrotra. He's no more, okay, but he was one of the most brilliant chemists of his time, very widely respected, okay, and this thing, he put in the tartrate, and when he did that, okay, he was able to make the chirally active epoxide. Okay, so this compound with the hydroperoxide was actually promoting the epoxidation of olefins. Okay, and so he was able to make the chiral epoxide, and you can imagine how important that is, because chiral epoxides can then be opened up in many different ways. You can form carbon-carbon bonds, and you can do that stereospecifically, okay, because you have made it chiral. Okay? But there was also a shortcoming in whatever he had done, in the sense that it was too restrictive. He could only do it with substrates like this, which is allylic alcohol. So he could take any allyl alcohol and it would epoxidize. But if you just took a regular olefin, okay, it would not do it. Okay? And even if you had other substituents on the olefin, it didn't work. So it was very, very restrictive. But nonetheless, it led to a huge explosion of interest, in this work, because till that time, nobody had ever done an asymmetric oxidation. This is the first, Sharpless was clearly the first who accomplished that, and that's why he got half the Nobel Prize, because it was quite a remarkable piece of work. But this is something that all of us should note, that okay, one is that I get a good result and I can gloat over it, okay? Or I can say, look, I mean, it's too restrictive, and what can I do next? Okay. So again, he drew on the other very interesting thing that Sharpless did, was that tartaric acid as such, you can imagine, I mean, it's not very, it's not soluble in organic solvents. Like he was doing these reactions in an organic solvent, like methylene chloride. So what he did was that he formed the half ester or the full esters of the tartaric acid. Okay, so the esters became soluble in organic solvents. So quite the opposite of William Knowles, who sulfonated his ligand, to make it water soluble. Here we have a case where the compound is water soluble, and Sharpless went the other way and made it organic solvent soluble, so that he can carry out his reaction. By the way, I mean, this, for example, this approach, although Sharpless at that time had said that it works for allylic alcohol, because he was interested in making epoxides, but subsequently, for example, just to show you, identical. I mean, whatever Sharpless did, the same reagents, etc., were used, and this molecule could be easily made. And what they did was that they were able to oxidize the sulfur, to the sulfur oxide, and then this becomes a chiral center. And this is known as omeprazole. You would have heard it's an anti-ulcer drug. And the S-omeprazole is supposed to be the one which is relatively free of any side effects. So this was a very big accomplishment by the Sharpless methodology, and it also showed that one need not be only focused, just because he had worked on epoxidation, that I only look at that. I can look at it as an oxidizing agent rather than only as an epoxidation agent. Okay, so that's how you many times you improve the scope. By the way, I must also tell you that this also happens. Sometimes everybody gets so caught up with chiral drugs and great esomeprazole is wonderful, but there are also people who kind of take a step back and ask, really, is all the data so supportive of a chiral drug being a preferable drug to the racemic version? And in fact, I was reading this paper by some Australians, and it says single enantiomer drugs, elegant science, disappointing effect. So it's not as if in every case the evidence was so convincing that there is a side effect, or this. These people said at least in omeprazole there was virtually no evidence, and they were actually discounting and basically saying that it's not worth doing it because people were just selling these optically pure drugs at a premium at a much higher cost. So he said, why are we doing all this? There's no evidence there's certainly no strong evidence. Of course, this would be a minority view because today nobody will go back to racemic drugs. I mean, if you know that there is an optically active form, and that optically active form is specifically the active portion, then people will say, why should I unnecessarily create a confusion by making the racemic form? We don't know what effect the other thing might have. So that's an issue. But remember that many of these things sometimes it can spur controversies.